So here's a problem straight out of your physics textbook, and you can find it on 392. But here's what we're going to do. So let's assume that you actually have a sound or a light wave, and you run into a problem like this. Like a sound wave has a frequency of 192 hertz. What is the wavelength? Now you're obviously panicking because if you look at our wave speed equation, v equals to wavelength times your frequency, right? That's our wave speed equation. We know that the longer your wavelengths you got, and the more frequent they are, the faster your wave is traveling by you, right? So if you got a longer wavelength, or if you have a very high frequency, this wave is going to come by you faster. And both of these dictate something very much like we have x equals, v equals x over t. This one dictates like the timing of the wave. This one dictates like your displacement or x factor, okay? So notice you still have kind of that idea here. But note here we give you a sound wave and we're not giving you either one of these. Like we don't give you a velocity or, I mean, we just give you this frequency, right? But we're asking for wavelength, right? So we want to find this, but we don't know what the velocity is. Or do you? Here's the thing. The key thing you need to tune into is what type of wave you're dealing with. Here we're dealing with a sound wave. This is easy. We know that our normal sound wave is 340 meters per second now. Do note, I may have accidentally said it was 330. It's actually 340. I'm sorry about that. 330 is actually when you're at 0 Celsius, and I'm assuming, well, we'll get into more of this later, but 330 is only a value you should use if you're at freezing. And we're not freezing here. This is a normal day, so this is at 20 Celsius. So this is actually one of the factors we talk about, factors that affect that sound wave. But we'll talk more about this later. So for now, use this value, okay? 340 is the velocity of, the speed of sound, okay? This is what you're going to consider. This is your sound barrier and everything else. So here's what we're going to do. We know this value. So we know V and we know frequency. Now we just need to rearrange our equation again. For wavelength, that's easy enough. Wavelength, if we divide frequency on both sides, is velocity divided by the frequency. Okay, so now we can just plug everything in. 340 meters a second divided by our frequency of 192 hertz. And remember, this is inverse seconds. So these inverse seconds is going to cancel each other out. So you'll be left with a length. Okay, let's do this. Hopefully everyone can see that. So note, we went ahead. First, we got the speed of sound, 340 at 20 Celsius. Okay. Sometimes the book will direct you on which one to use. This one, I know it's just normal air, so I'm not going to use this one. And then after I go ahead and rearrange my equation, I plug in both my values. Now I'm going to go ahead and just use a calculator. Figure that out. So 340 divided by 192 is, let's see, 340 divided by 192 is 1.77 meters. There. Okay, so I have to look very carefully into what wave I'm using, looking at the speed of sound, okay, and really thinking about what type of wave I'm considering here, okay? All right, hopefully this helps. I'll see you next one.